right, as a warm-up, let's do the following. Let capital F arrow, so we're about to define a vector field. F of xy equals angle bracket x over 3, comma y. All right, let's find the line integral over the line or the curve C1 of f dot dr. Don't forget the arrows, please. And we'll also find the line integral over a second curve C2 f dot dr, and simplify as much as possible. And to finish the question, we need to describe C1 and describe C2. So C1 is in the xy plane. We've just got this line segment that goes from the origin to the point 2, 2. So that's the curve C1, or the line C1. What about the line C2? So this will be in two pieces. So start at the origin, move to the right, then from there move on up, and so we'll get to the, so that's C2, and we'll still get to the point 2 comma 2, right? So right here, of course, that point would have to be 2 comma 0 if we travel fully to the right and then fully up. So to answer this question, for the first curve, for C1, let's go ahead and parameterize and write as a vector function. So r of t is equal to 2t comma 2t, where t goes between 0 and 1. We'll just point out that another option could also do this. You could do r of t is equal to angle bracket t comma t, but then t would have to go between 0 and 2. Now that works. Okay, this is technically completely fine, but we're just going to stick with this parameterization instead. Why not? Maybe we'll just cross this out. It works, but we don't want to get confused. And then we've got f of r of t when we compose. Let's see. So it's supposed to be x over 3, so in other words, 2t over 3. And then we're supposed to have the second component supposed to be just y, so we'll just have 2t here. Then also looking at how r of t is written, we can get r prime of t. So differentiate each component, you have 2, and you get 2. All right, so then the integral over C1 of f dot dr equals the integral, t goes from 0 to 1, 0 to 1, of, when we dot, we'll have 2t over 3 times 2, so we'll have 4t over 3, plus, and then 2t times 2 will be 4t dt. In the end, this is going to become the number 16/3. Now, the second part, okay, so that's for C1. Now let's find out what happens with C2. So we need to parameterize. Unfortunately, with these two line segments, the way they're located, just based on the shape, we're going to have to parameterize piecewise. So the vector function we can also describe piecewise here. So we've got, how about t comma 0 for, let's do 2t comma 0. 2t comma 0 as t goes between 0 and 1. And then for the vertical part, let's see, the x-coordinate is just 2, but the y-coordinate goes between 0 and 2. So this should be like a 2 times t minus 1. I think this is going to work. 1. Let's just check if that's going to work. Plug in 1, and that's 2 times 1 minus 1. 2 times 0. Okay, that you get the 0 that we want. If you plug in t is 2, 2 minus 1 is 1, 1 times 2. Yeah, that's going to work. Okay. All right, so there we have a parameterization. Now let's go ahead and we need to do this thing, composing f and r, but in two different pieces, right? So there's sort of what we do if t is between 0 and 1, and then there's what we do, let's say over here, if t is between 1 and 2. We just got to break this into the two separate pieces. So between 0 and 1, f of r of t is, so we are composing, again, the function x over 3 comma y with 2t comma 0. So 2t for x and then 0 for y. So 2t over 3 comma, and then for the y we're plugging in 0. Over here, when we compose f of r of t, we're going to use 2 for x and then 2t minus 2 for y. So we'll have, okay, 2 for x, so 2/3. And then, let's see, then we just have y, so that's going to be 2 times t minus 1, or 2t minus 2 to write it, distribute it out. We also need this part, we need the r prime portion, so r prime of t, based on the first part, should be 2 comma 0. And then r prime of t for the second part should be, well, 2 differentiates to 0, and then 2t minus 2 over here will differentiate to a 2. So when we now set up the integral this time, the integral over c2 of f dot dr, hope it makes sense, we actually have to turn this into two dt integrals. There's an integral from 0 to 1 dt, and a separate integral from 1 to 2 dt. And so what goes in this spot should be the dot product of those two things, which should be, well, 2 times 2t over 3, so 4t over 3. Oh, that's a lot more space than I guess we really needed. Let's just push things over here. Then over in this space, we need to dot these two vectors together. Fortunately, 0 times 2/3 doesn't give us anything, and then 2 times 2t minus 2 will give us 4t minus 4. Now let's just go through our integrations here. So we'll have 4t squared over 6. Let's clean that up. 2t squared over 3 at 1 and at 0. And then over here, let's see, 4t squared over 2, so 2t squared minus 4t evaluated at 2 and at 1. So we'll have 2/3 plus, over here we'll have, see, plug in t is 2 first, so 8 minus 4 times 2 is also 8, okay, minus, and then plug in 1, so 2 minus 4. So we have here 2/3 plus 0, let's not write that, minus negative 2, so plus 2, so plus 6/3, so we get 8/3. Now if you'll take a look, the final answers are different. So over here we had 16/3, here we have 8/3. Okay, the fact that the final answers are different is rather important for us. We should mention here that because the line integral over c1 of f dot dr, it did not give us the same number as the line integral over c2 of f dot dr. The vector field f, capital F, is not conservative. So there's no path independence, in other words, right? Conservative and path independence should be the same thing. So there's no path independence. Now it did matter that for this, what we did was we detected that there's no path independence. It did matter that both of the lines started and ended at the same place. So both of these curves, C1 and C2, started at the origin. Both of them ended at the point 2, 2. Okay, so let's recall, because we'll be practicing it. Let's recall from last time. The fundamental theorem of line integrals says this: if vector field f is conservative, Okay, in other words, there's a function. There is a function, or there exists a function. There's a function lowercase f such that capital F, the vector field, is equal to the gradient of lowercase f. Okay, and C is parameterized by a vector function, so little r of t, with t going between a and b. Then we create this new alternate way of computing a line integral of the vector field. So the vector field, capital F, dot dr, integrated over the curve C, we can do the traditional thing with the whole dt business, or we can instead, this is what the theorem is saying, is you can just take that potential function, lowercase f, and compose that with the vector function which represents the parameterization. So f of little r of b minus little f of little r arrow of a. Okay, there's the reminder of the fundamental theorem of line integrals.